Hey, good evening, class. Mr. Bean here for Honors Physics. We're now going to move into lesson 12.8, which is mirrors and reflection. Uh, this will be video 1 of 5 to do this lab here. And this will be the last thing we do before spring break. Okay, so anyways, part 1 here is called reflection with flat and concave mirrors. Now here, imagine a circle here, and this of course is normally, we would know this to be the radius of a circle, but in terms of mirrors, this is called the radius of curvature, and this is called the center of curvature imaginary. Now take a look at radius of curvature. Let's see what that really means. So up here, calculus. Okay, radius, curvature, and radius of curvature. So it says here, consider a plane curve defined by the equation y equals f of x. No, I'm just joking. Okay, we don't have to worry about this. Okay, suffice to say that the radius of curvature is the radius of the sphere from which a mirror was cut. So imagine this is a sphere here, or a circle, and we cut away all this part here, and here we have a mirror. So the radius of curvature is really the radius of the original sphere or circle, if you will. Now, there's an important term which is called focal length. Okay, so we're going to have here F is equal to focal length, and we want to figure out what that means here. So we'll talk about that here in a second, but there is a relationship. Focal length is going to be a point that's halfway or half the radius. So we could say focal length is half radius for right now, okay, just until we get going here. All right, from last class, we understood that if we had a flat mirror here, and here we had the incident ray, when it bounces off, this is the angle of reflection. So if I was to do some annotation here, this here will be the incident angle here, which is right here, and this here will be the reflected angle, okay, like this here, reflected angle, okay. Okay, so incident, okay, reflected. So we measure it from with respect to the normal. So the law of reflection states that the angle incident must equal the angle reflected. Okay, this is the law of reflection. Okay, let me go ahead and pause here for a quick sec. Okay, so let's go ahead and continue on here. Here we have a flat mirror. Okay, so let's go ahead and take a look at this simulation here, and let's see what the flat mirror is. So we'll go ahead and hit begin. So all the incident rays equals reflected rays, and I can even change the angle here a little bit. There's a protractor. Okay. And we can kind of see what's going on here. Okay, we can change the angle here. So this angle here is 60 degrees. And so the incident angle is coming in at 60 degrees. And it looks like it's bouncing out at about 30. Okay, so 90 minus 30 is 60 degrees. So incident angle equals reflected angle. Okay, on this flat mirror here, so sometimes we have an object that's right here, and so the rays are coming in here, bouncing, and they hit our eyes here. Even though the object is here, it appears that virtually the image is right here. If there's like another dimension, we could reach in and touch what this is right here. So that's a flat mirror. This will be the virtual image, and this DI is called distance of the image. And this here is DO, which is called distance of the image. So distance of the image is the actual distance with a ruler, what the image is from the actual mirror. DI is a virtual measurement. It tells you, it gives you a virtual or mathematical or kind of a fictional distance of where the image would be in a virtual reality situation. Okay. All right, now we're going to come down here and talk a little bit about concave mirrors. Okay, concave mirrors. Okay, and let's go ahead and take a look at this and see what we got. So you're going to do this too. We're going to click on begin, and here we have an ideal concave mirror, and we can see that the incident rays are coming in parallel. They hit the mirror and they kind of bounce to kind of like a point here, like right here. So if I was to show a ruler like this, okay, this point right here where all the lines seem to hit is called the focal length. Now we talked about that earlier. So this is F, which is the focal point. That is right here. And according to this diagram here, the focal length is about, this is 6, this is 7, this is 7.5. Yeah, maybe we could say maybe 7.35, 0.35 meters, okay? That will be the focal point. And then the radius of curvature should be 2 times the focal point. Okay? That's the relationship between focal point and the radius of curvature. The focal point, again, is after the light rays strike the mirror, is they come to a focal point or a point where they all converge. That's called the focal point. So let me go ahead and hit pause here, and we'll continue on. Recording. All right, so you'll want to go to this link here and do what I just did with the ruler, screenshot the ray diagram with the ruler and tell me what the focal length, and copy and paste it in here. Okay. Again, here's some more illustration of the focal length for a concave mirror, and here's the power. Power of the mirror is 1 divided by the focal length. Okay. So now, if so here, each box here is 1 centimeter. Let's determine the focal length. Okay. So let me go ahead and let's do some annotation here. And so I'm going to have, and let's say I'm going to have some kind of an object, let's say right here. Okay. So this is the object here. And so we're going to draw some focal lengths here. So let's see what we got here. So what we do is called a ray diagram. So I'm going to go ahead and kind of draw this as parallel as possible. It hits the mirror here, and it's going to bounce through the focal point here like so. This one here goes through the focal length here, hits the mirror, and then goes parallel. And then where they intersect here is where the image is going to be formed. So in this case here, here's the image. It's upside down, but here's the focal length. So I want you to estimate and tell me how far is the focal length. Okay, and this will be the end of part 1.